So my background is in university teaching, so I've been an academic for pretty much forever. I've got a PhD in AI for games, and from that I actually published my first book about my PhD, and it was looking at emotions and how to use emotions and replicate sort of real emotions to make decision making in artificial intelligences. Anyway, I finally gave away the academia and started my own business. So I teach online, and I teach, where's that slide go? There we go. Beginner's Guide to Machine Learning in Unity, which is in Udemy. Who's heard of Udemy? Okay, great. So you'll find me on Udemy and also holistic3d.com. And last week, my new book also came out, which is Holistic Game Development. And I promise this isn't sort of a whole promo session about me, but I worked with Unity to collaborate on developing this. So it's a sort of a textbook, I guess, for university students, for complete noobs who want to get into using Unity. All right, so let's get on with this because I don't have a lot of time, and machine learning is a very complex topic. So who are programmers in here? Okay, who are designers in here? Who are mathematicians in here? Oh dear, I'm really scared of you. Who are statistics people in here? Okay, well, machine learning is all about mathematics and mostly about statistics, and maybe some of you probably know a lot more about this kind of area than I do, because statistics isn't a really strong area of mine, but I really think machine learning is very cool. So I'm going to promise you that there's not very much mathematics in here, and if I can, I'm going to give you a complete understanding of what machine learning is without discussing any mathematics. Okay, so what is machine learning? We're going to look at that in a moment. We're then going to go and have a look at genetic algorithms, which are probably my favourite type of machine learning. We'll talk about that. Artificial neural networks. And then we'll lead that into an area called Q learning, which will then finally take us into the ML agents that Unity are currently developing. So often I get asked, what is machine learning? So I've got a course on game AI, and I've also got a course on machine learning, and people don't quite understand the difference, but there's a massive difference. So AI is this huge domain and encompasses so many different things. Okay, so like robotics, planning, vision, and there's a few sub areas in there, speech, text to speech, speech to text, expert systems, natural language processing, so text generation and also answering questions, and finally we get to machine learning. So machine learning is this tiny little area of artificial intelligence, and even within machine learning we have deep learning, unsupervised learning and supervised learning, and the ML agents actually fall into the categories of deep learning and supervised learning, which you're about to learn all about. Okay, so what is machine learning? Well, it's a system that has the ability to automatically learn and adapt to its environment from experience rather than being explicitly programmed. Now, at first, that kind of is a difficult concept to get, because if you're a programmer, then you think, well, I program everything, and whatever the agent does, it behaves because of how I programmed it. But with machine learning, you actually sort of start out with this random being that has random behaviours, and it starts to evolve its behaviours itself from its own experience in its environment. So here's a little demo. I hope this video works, and we'll get back to this set of walkers, but this is a genetic algorithm trying to learn how to walk, and you can see it's fairly hopeless. And we'll come back and have a look at how he's going a little bit later, but it's quite challenging. Kind of looks like he's had a few too many drinks, doesn't he? But when you learn about this is a genetic algorithm, when you learn about that, you think, whoa, this is absolutely amazing what that's trying to do. So machine learning is kind of inspired by two areas in sort of the natural process. First, we have evolution. So evolution works on the process of natural selection. where something behaves in a certain way and survival of the fittest type stuff, and they're the ones that then go through. And that's what genetic algorithms all about. And then we also have behaviouralist learning theories, which is the kind of way that kids learn, okay, from feedback from the environment and that sort of positive and negative reinforcement. And that's what neural networks are about. Okay, so let's go and have a look at genetic algorithms. I know I don't have a lot of time and I don't want to rush through this, but there is kind of a fair bit of content to get through. So with a genetic algorithm, we start with a population of agents, and by agents you could imagine as like one NPC in a game, and it's programmed to act randomly within its environment. Okay, so the whole population of these agents is created and they all act. The actions of the individuals are then assessed against some particular criteria. Okay, so they might be the agent that lives the longest or the agent who gets the furthest or whatever your criteria are. Now, the ones who are the worst performers get culled. So this is just like in real evolutionary terms. And the fittest ones that still survive at the end or get past your test, they actually are used to breed a new population. And then you get rid of all the old ones and the whole new population comes in and then it acts. Okay, so let's have a look at an example. So here's an agent, and the way that you program them is you give them a sequence of what we call DNA. Well, you know, just like evolution. Within the DNA, each box in there is called a chromosome. Okay, pretty much, if anyone's familiar with biology, like our sort of stuff works. Now, there's nothing fancy about this DNA. It's just an array. So if you're a programmer, it's an array. It can be floats, ints, strings, Boolean values, doesn't matter. So the chromosome is just like one index in your array. So we start by getting our agent and we put it in a particular situation. So here we've got this little blue bird, and he has to make it from the left to the right through this maze as best he can. Now, to simplify this, what I'm doing in this example with the DNA is we're going to program the DNA so that it only figures out how much force to apply to the bird up and down. So the bird's just got this constant velocity, it's just going to keep going like that, but the genetic algorithm is going to figure out whether it should be going up or down so it can avoid all of the obstacles in the environment. Okay, so when you start to create any sort of AI, or machine learning I should say, think about how you yourself would solve the problem. And then possibly, if you're a programmer, you might break that down into an if statement. And there's a lot of jokes on Facebook in machine learning when they see something happening that they say, oh, we could have done that with an if statement. And a lot of the time you can't just do it with an if statement. The stuff you're going to see today, you can do with an if statement. But the thing is that these really complex systems would be a massive if statement. And sometimes you might not quite know exactly what the program should be. And the whole point of machine learning is that it figures out what it should be doing rather than you telling it. So you just give it some really simple instructions. So if we were to program our little blue friend here, we might say, if you see the ceiling, then you've got to move down. If you see the floor, you've got to move up. If you run into one of the arrows pointing down from the ceiling, then obviously you want to move down. And if you run into one of the arrows like this, you want to move up. So that's our simple if statement. So where does the DNA kind of come into this? Well, each index into the DNA is giving the bird instructions of what it should do when it runs into those things. So in that first index, that's going to have a force value in it, so a float value, which tells the bird where to go if it hits or detects the ceiling. The same as if it detects the floor, if it detects a top arrow, bottom arrow, and then if it detects nothing. So this little bird, he's just got a few ray casts going on in Unity to see if he hits something. So we now can change our if statement to something like this. If we see the ceiling, then we have to do what's in DNA box 0. if we see the flaw, we're going to do what's in DNA box 1, etc. Okay, just ignore these boxes here, they're not meant to be there yet. So we start with a population of little bluebirds, and they all get random values put into that DNA. Okay, so one of them might detect the top and then still decide to go up, in which case he's kind of going to get stuck up there, which means he's not a very fit little blue bird. And then some of them will randomly get the right forces in that DNA sequence to actually push them forward through that maze. Okay, so we run it and the birds act and they do whatever their DNA tells them to do. Some get stuck in the corners and that type of thing. Now our fitness function in this case is going to be, well, we want the population that got the furthest, okay? So they're the fittest guys in this maze. So what we do is we, go the other way, grab those two, or however many there are. Usually you take about half the population that's at the top end of fitness. And what we do is we breed them together. So this is their forces for up and down based on what they've detected. You don't actually add them together or average them. What you do is you take some of the chromosomes from one parent and some of the chromosomes from the other parent and put them together. And I keep swiping in the wrong direction to get the offspring. So in this case, I'm taking the first 3 from that bird and the last 2 from that one, putting it back in to get our offspring. Very similar again to the way that real DNA gets replicated. Okay, so let's have a look at an example. Now, each time this resets, it's a new population. So you'll see them all start over in the corner there. Okay, so you can see that the furthest are getting grabbed and there's less and less starting to get behind in there. So they're learning. Each new population is starting to retain all those good DNA or chromosomes that help the birds get right through it. And eventually, we're up to like generation 18, 19 there, we were getting there where we almost had a completely fit set of little blue birds. Okay, so here's another example of a genetic algorithm which just has 2 chromosomes, and the idea here is we want to keep our agent on this platform. So the agent is going to have different turn amounts based on whether he can see the platform or whether he can't see the platform. And again, let's just simulate this. Initially, they start running off the platform. They're going to be culled. They're not very fit. And then eventually, they're going to start to go in the next, few generations. Oh, I'm going to have to turn when I can't see the platform anymore. Isn't it cool? I love genetic algorithms so much. You can play around with them and have a lot of fun. Okay, so moving on. Let's see how our walkers are going. So I kept this running for like 6 hours, and after 3,238 generations, he's not too bad. He still looks a little bit drunk, but so you just saw the like the DNA for the simple little birds and Ethan that was running around on that platform. Imagine how many chromosomes you need to store all the angles of all of those what are they called, bones, joints in this guy. Now the fitness for this guy is how far he keeps his head above the rest of his joints and how far he actually gets or how long he sort of exists before he falls over. And even after that many generations, we're still not got something that's really quite intelligent looking. And it does, if you've got a real genetic algorithm and an actual real problem to solve, it will take an awful lot of generations and a lot of training to get it right. So genetic algorithms, like in real time we've just seen, isn't necessarily something that you're just going to apply straight into a game and set them all to be random and let them go, because you've got completely unrealistic behaviour that's going on. Where you might use them in a game, in this case, is an army of a population that have to learn to battle against the player. And so that as they're destroyed, new populations get generated with new strategies to try and battle. So they're, in a way, I guess they're evolving and adapting to their environment. Okay, artificial neural networks. So they're inspired by the way that your human brain has been formed, and it works, and they're used in deep learning. And in fact, deep learning is a term that came into being, I don't know, about 5 years, a bit longer ago. And deep learning really was just a name that replaced the word neural network. I'm getting told that I've got much time here, so I'll just speed through. But it's used, neural networks are used in ML agents. So if you know anything about the biology of the human brain and the neuron, the way it's structured, you have a neuron, like you can see here. It has this area called a soma and these dendrites that are on the end. Now, signals come into the soma, and then once enough sort of electrical pulse or whatever fills up inside, then it then passes the signal on to the next neuron. So if there's not enough sort of signals coming into that neuron, it won't fire, and therefore the pulse will not be sort of transmitted along it. So the more pulses that get transmitted along your neuron, along the synapses to the next neuron, you then form these very strong pathways in the brain, which then constructs our behaviour. Now, our scientists took this and they created a perceptron, and the perceptron is pretty much the electronic, computerized, programmed version of a neuron. Again, I'm not going to go into a lot of detail because I don't have much time here, but the way a perceptron works is that it has some inputs, okay, so they're like the dendrites. So let's say we're going to put a 1 into that input and we're going to put a 0 into that input, and then we want some particular output. So you don't leave perceptrons do their own thing. You actually say, this is all your input, and all this input has to produce this set of output. So you have this desired set of output for behaviours. So we plug through the 1 and the 0 in this case, and let's say the output is 0.8. That would give us an error value of 0.8. That 0.8 then gets propagated back into the perceptron and absorbed into the perceptron. Its weights change, and then its calculations that are doing are updated. Bear with me. I know, without a lot of mathematical background. Anyway, let's just quickly zoom through this. So the structure of an artificial neural network pretty much looks like this. It's a whole set of these perceptrons all linked together where these signals are being sent through, and there's output being created, an error is calculated, and then the error is actually plugged back into the neural network through a process called backpropagation, and that updates the weights and it readjusts that brain. So here's an example of artificial neural network being used to create procedurally generated animation. So this was created over hundreds of thousands of training sets of observing real player behaviour in the animations of characters, and then it can fill in the gaps, say, between, say, a walk cycle and a jumping cycle very smoothly and automatically using the neural network. Okay, I'm probably starting to run out of time, am I? Yep. So one way we can train a neural network is that it can observe actual human players. So this is the little go-kart thing that I put together, and you drive around this track and it records the distances from 5 different angles of where you're about to hit the sides of the road, and then determines, or at least it records, what the human player is doing. Very similar to the way that they train driverless cars. Okay, so they take all this data from real drivers and run it through the neural network over and over again to train it. So this go-kart gives you a data set of the distances from all the different angles, and then the direction that the player actually turned, We plug that into the neural network and train it, and then you end up with a character that can automatically drive around the world. And because it knows how to turn based on the distance to things, you actually put it in other environments. As long as there's something to collide and move through, it will be fine. So it can adapt in that way. ML agents are based on what's called reinforcement learning. Reinforcement learning is very much behavioural, so positive and negative reinforcement. So what happens in this, in what's called Q learning, which is reinforcement learning, is that you have states of the world given to your agent. The agent then thinks about the states of the world and then comes up with some particular action that it's going to take based on those. Now, actions don't happen all by themselves before you get any feedback. So an agent could do multiple things before it gets the feedback. Okay, so we have a whole sequence of these state action sets that the agent runs through, and then at some point it will fail or succeed in what it's doing. When it does, it gets a reward. So it can be a negative reward or a positive reward, which is propagated up to the system. And that reward is basically attributing blame to a particular action. Now, you can't put the same blame on every action in a very long sequence. So what it does is it sort of gives a lot of blame to the last action, and then as you get further away from the consequence, there's less and less blame attributed to something like you did half an hour ago. Same as human behaviour. And that is what is in the ML agent. So here's a bit of an example of a balancing ball. If you've looked at the ML agent stuff, you'll see that there is a Unity example of this. Now, this platform is trying a sequence of actions, and it doesn't actually get any feedback until the ball falls off. So it's very stubborn at the moment, and it just keeps going that way and that way and that way because it does. Anyway, this direction that it's going in is constantly getting bombarded with negative reward, negative reward, negative reward, and eventually it decides that that's probably a really bad thing to do, and it will start to tip the other way. Here we go. There. That's really cool. And so that's pretty much what the ML agents in Unity does. You've probably seen this example. They're doing it on 2 axes. I was just doing it on 1 axis. And when you add more axes, you add more states of the environment and actions, and you need a lot of training for it to figure it out. So how do you get started with ML agents? The best way is to go to GitHub and look through the documentation. Has anyone tried the ML agent stuff? Yeah. It changes often, and so it's really good to actually go in here and get it where it's been updated and set it up from there. But do read through the documentation because it is very helpful. What I do want to point out from having shown you a bit about machine learning is the actual brain of the ML agents and the important parts of that brain. So we talked about that you need to collect observations from the environment, and there is a method in there that you need to fill out with the different observations that you're getting from the environment. So in this case, you're looking at the game object's rotation in the Z and the X, and also where the ball is. Okay, so from that gets plugged into the brain. You then have an action method which tells the agent how to react based on what its brain tells it to do from observing the state of the environment. And you can see in that code there that it will keep rotating and acting, and then if the ball has fallen off the platform, it gets a negative reward. Otherwise, it keeps giving itself a positive reward, and that's the part that actually starts training and setting the rewards to those state action sets. Finally, when the ball does fall off the platform, you need to reset the agent's brain so that you can start the whole sequence of actions again until the ball falls off. And so for inside of this agent class, we have an agent reset where you're basically setting the platform back to flat and the ball back to wherever it starts, just above the platform. Okay, very quick overview. So what I'd like to really tell you and for you to take away from this is that the ML agents set is very complex. Machine learning is very complex. You don't really learn it in a university until like master's level. And as much as I really love Unity, what I would say if you're interested in this field is that you go back to basics and try and program these things for yourself. And the genetic algorithms, the programs in here might have already got a bit of an idea how you would program that. It's not that difficult. It's also from basics in my Udemy course. If you have a look in there, it's you don't use ML agents until later in the course. You're actually programming hands-on, creating a neural network, creating a genetic algorithm. Okay, thank you for your brains and your time. I hope you got some kind of sense about what machine learning is and an appreciation of how powerful it could be. Thank you.